So last time we introduced the LCM method, okay, the lumped heat capacitance method, which is a method that will allow us to solve for transient problem in case the temperature variation with space is not important. And we said that to determine if LCM can be applied or not, we just have to calculate the byte number. If the byte number is smaller than 0.1, then we can neglect variation of temperature with space. But if byte number is larger than 0.1, we need to go back to our differential equation and consider the variation with space. Now, the general differential equation will take into consideration the presence of generation. But here, for a first case, let us consider 2D variation, transient variation with no generation. So the equation will be reduced to 1 over alpha del T, derivative of temperature with respect to time. So this is the transient term. And since we have two dimensions, so temperature is varying in 2D, then we'll have second derivative of T with respect to X plus second derivative of T with respect to Y. Now, in order to solve for such equations, okay, in general, we can use analytical techniques, but with complex geometries, analytical techniques will be challenging. So sometimes we don't have analytical solution. So we go to numerical technique. As we have seen, we introduced numerical technique in chapter 4. So the whole idea will be to transform these derivatives into numerical terms. So for example, we can write, instead of derivative of temperature with respect to time, we can write delta temperature over delta T, okay? So then we say that we will discretize time and space. So instead of dx, we work with a small step of in space delta x. And instead of dy, we'll work with delta y. For example, okay, if we say that we will discretize time with a step of 0.1 second. So if we take delta t to be 0.1, then we can say that the times will be 0, 0.1, 0.2. So this is the step. Always we add the step of time delta t. So we will solve for variation of temperature for times with step 0.1 second. And then we can say that the time will be written as an integral, as an integer p times delta t. Okay, so it's a multiple of delta t. Now, how to decide on which delta t to use or which delta x, delta y, we'll discuss together in the coming slides. So now, also, we can replace the second derivative as we have seen together. So first we replace, as we said, the derivative of temperature with respect to time. And it's equal to T P plus 1. P plus 1 means at a time step, as we said, P is the number of time steps, okay? So at any, if we consider now for between, for example, 0.2 seconds and 0.3 seconds, so P will be equal here to 2. And here it's equal to 3, okay? So if I take P equal to 2, for example, then Tp plus 1 will be T, the temperature at 0.3 seconds at the center of a certain cell. If you remember in chapter 4, we divided the space into several columns, several rows. And for each cell, okay, the temperature at the center of the cell will represent the temperature in the cell. So I can say that the derivative of temperature with respect to time for a cell Mn is equal to Tp plus 1 at Mn minus Tp at Mn over delta T. So this is how I can transform this derivative form into numerical form. And I replace in my differential equation. Okay. Now I will do the same for the space term. So for the space term, I can replace the second derivative with respect to x by the following term, which is the temperature in cell m plus 1 and p. And to understand how we got this, if you take a cell, this is your cell, okay? And we have at the center of the cell Mn. So this is the index of my cell Mn. If I take a cell just before, okay, for a cell just before, I have the index is M minus 1 N. And for a cell just after, it's M plus 1 N. So now if I want to get the second derivative will involve these 3 points. And I can replace the second derivative of t with respect to x by the following formula, which is Tpm plus 1n plus Tpm minus 1n minus 2 Tpmn over delta x squared. I can do the same along y. Along y direction, I have the cell above. The cell above has index Mn plus 1. And the cell just below has an index of M and minus 1. So we have seen last time together in chapter 4 that I can replace the second derivative by this numerical form. Okay, so I just have to write, instead of second derivative of t with respect to y, I can replace it numerically by temperature at time p Mn plus 1 plus temperature at time p Mn minus 1 minus 2t Pmn over delta y squared. Now, as you can see, we decide to put all temperatures in the other side, yani for the second derivatives, all temperatures are considered at time p. But you can tell me why we selected time p, not p plus 1? Because it's right that you can put here, you have the choice. You can put at time p, you can put at time p plus 1. This is what will tell you what to do is the type of method. This is called explicit method. In the explicit method, we describe, if you want, we put just Tp plus 1 in the transient term, derivative of temperature with respect to time. And in all other terms, we put temperatures at previous time step. This will simplify the solution, because I can consider that the only unknown in this equation at time p plus 1 is Tp plus 1. And I can express in this way Tp plus 1 function of all temperatures in previous step. So this is called the explicit technique. The solution of this in this method is easier than the implicit. In the implicit method, you can put, okay, temperature here, for example, at Mn, you can say, I want to put T at P plus 1. Okay, and then the coefficient of Tp plus 1 in the equation will change. And we have techniques that can be developed to solve implicit method. So when you go, if you take a CFD course, you will see different techniques, how to solve in explicit, how to solve in implicit, etc. But here we'll consider together the explicit method. So the subscript P is used to denote the time dependence of temperature, and the time derivatives are expressed in terms of the due difference in temperatures associated with the new point at time p plus 1 and at previous p times. Hence, calculations must be performed at successive times separately by the interval delta t. And just a finite difference solution will restrict temperature determination to discrete points in space. So here, you cannot solve for any x, any y. You need to divide your space into discrete points and solve at the center of your cells. Now, once you have temperatures at the centers of your cell, you can do linear interpolation, okay, in order if you want to solve in between. But when you use this method, you are assuming that in one cell you have the same temperature, and in the cell, an adjacent cell, I have another new temperature. And actually, it's not the case. The temperature will vary within the cell, okay? But in order to use this method, we need to use a certain assumption. And in general, once you determine temperature at different nodes, you can do like, if you want interpolation techniques to determine temperature variation between nodes. If you want to draw the profile of temperature. And if you have several points, if the points are close enough, for example, and you have considered temperature at different nodes, you can do linear interpolation and join the points to get the temperature profile. Okay. So this is the explicit form, as we discussed, of the 2D transient equation with no heat generation. Now, how to continue with it? Okay, we will develop this equation. If we develop this equation and we assume that delta x is equal to delta y, okay, we can come up with this relation. Let us derive it together. If I go back to the previous equation and I say delta x is equal to delta y, I can replace here delta y by delta x. And what I will do, I will group, okay, I will group all terms having the same coefficient. And now, if I multiply the two sides by delta x squared, so this term will cancel out, this term will cancel out, and I will have here delta x squared. Okay, so to start with, I need to determine the coefficient of each of my temperature. If I take the term Tmn at time p plus 1, the coefficient of this term, I have just Tmn p plus 1 just here. I just have it in one place, which is here. So the coefficient of this temperature is delta x squared over alpha delta t. Now, if I consider the term Tpmn, this term is figuring out several times in this equation. I have Tpmn here. I have it also here. And I have 2 Tpmn here. Okay. So if you want, if I take my temperatures to one side, if I take all my temperatures to one side, so I can take these terms to the other side here. Then I can determine what is the coefficient of Tpmn. The total coefficient of Tpmn is minus. So here I have a minus. So I will have minus delta x squared over alpha delta t. Okay. And I have here minus, so it will be plus 2. And plus 2 again, so plus 4. So I can say that the coefficient of TP M and P is equal to minus delta x squared over alpha delta t plus 4. Okay? Now for the other terms, for the remaining terms, TP m plus 1 and TP m minus 1 and TP m n plus 1 and TP m n minus 1, the coefficient from this side is 1. And if I take them to the other side, it's minus 1. Okay? So if I write my equation, okay, I will obtain that the coefficients are as follow. So here alpha نحن قلنا انه عندنا delta x square over alpha delta t. You remember we defined last time the Fourier number, okay? The Fourier number was alpha delta t over delta x squared. So we can say that in our equation, the coefficient here is 1 over Fourier number. 1 over Fourier number. Okay? So if you want, what they did, they multiplied the whole equation by Fourier. Okay? And we took TPMN here to the other side of the equation. So we obtain for this equation the following coefficient. So this term كان عنده 1 over Fourier. When we multiply by Fourier بيصير the coefficient of TP plus 1 MN بيصير 1. Okay? And if we consider the other terms, عنا كان الcoefficient هون 1 for all temperatures, then the coefficient will become Fourier because we multiply by Fourier number all terms. And for TPMN, okay, وقت أخذناها لتاني مال كان الcoefficient delta x square over alpha delta t minus 4. Okay, إذا بنتركها to this side and we multiply by Fourier number, we get 1 minus 4 times Fourier number. Okay, now as you can see from this equation, we can find the temperature at time p plus 1 function of all other temperature at time p. يعني أنا if I solved for time 0.2 seconds, I can deduce for 0.3 seconds, I just have to replace all temperatures by their values, and I will be able to calculate TP plus 1 MN. So this is the general, this equation is we call it the explicit form, which will allow us to solve for temperature at time p plus 1, function of all temperatures in adjacent cells at time p. Okay? Now, in general, we can have 2D, but also we can have 1D or 3D. Okay, if we want to apply the same approach in 1D case, in 1D case, things will be much easier. Okay, and we can derive together a much simpler form for TMP plus 1. Let us do it together to see how we get the expression of variation in temperature in explicit form in case of 2D. In case of 2D, first, my differential equation will just be 1 over alpha derivative of temperature, del of temperature with respect to time, equals to the second derivative of T with respect to x. And now to transform it to numerical form, as we said here, we just have one index if you want, m. There is no need for n because it's 1D variation. And if I consider this cell, I will consider that m represents the index at at the center of a certain cell. So if I take the cell just before the index is m minus 1, and if I consider a cell just after, the index will be m plus 1. And now, if I want to replace the derivative terms by numerical terms, I can say that I have 1 over alpha. We said that for derivative of temperature with respect to time, we can replace it by Tp plus 1 at m minus Tp. Okay, so I will write instead of this term, I will replace it by a numerical term. The numerical term will be T at time P plus 1 at the center of my cell. So this is my cell of interest here. I am solving for temperature in this cell. So in cell M, minus temperature in the same cell, but now at previous time, so at time P, over delta T, which is the time step I am considering, equals to, now we have seen together, okay, that we can replace the second derivative by the following expression. So first I consider cell before and cell after. So I can replace the second derivative by temperature at time P, because I'm using explicit method. An explicit method, all temperature from the other side will be considered at the previous time, at time P. So Tp m minus 1 plus Tp m plus 1. And we said we do minus 2. So minus 2 Tp at cell M over delta x square, over delta x square. Okay. Now you say, if I take delta t to the other side and I divide and so I multiply by delta t, okay, and by alpha, I get the following equation. I get T m P plus 1 minus TPM equals alpha delta T over x squared. And we said that this dimensionless term is called the Fourier number, okay? So alpha delta T over del x squared is Fourier number. So I can replace it by Fourier times, I have the temperatures from the other side are T P m plus 1 plus Tp m minus 1 minus 2 Tp. TPM. Okay, so now you can say that if I take this term TPM to the other side, what will be the total coefficient of TPM? The total coefficient of TPM is, already you have minus 2 times Fourier. And when you take this term to the other side, it's plus 1. So the total coefficient of TPM is 1 minus 2 times Fourier number. While the coefficient for TPM plus 1 and TPM minus 1 is Fourier. And in this way, you were able to express the temperature at cell M at time p plus 1, function of the temperatures in the adjacent cells and the cell M at time p. So if you already solved for time p, you just have to replace. This is why we say it's explicit, and we just have to replace directly, and we can explicitly find Tp plus 1. So Tp plus 1 is expressed function of temperature at previous step. We don't have any term here at P plus 1. In the implicit method, we can use here temperatures at time P plus 1, but the solution will be much more complex. Okay, so the accuracy of the finite difference solution can be improved by decreasing values of delta x and delta t. In general, smaller steps in time and in space will give more accurate solution. Of course, the number of interior nodal points must be considered increases with decreasing of delta x. So when you decrease delta x, this means that you will need more node points in order to divide your space. And for example, if I just have if I have 1 meter, okay? If I say that I will consider delta x to be 0.1, okay, we said that here, depending on the way you will consider your nodes, okay, in general, in the methods that we use together, the number of nodes will be equal to the size of the cell plus 1. And here, what is the size of the cell? It's 1 over 0.1. It's equal to 10. Okay, and the number of nodes is equal to the number of cells plus 1. So you have the number of discrete points that you will have is equal to 11. Okay, now if we consider now a smaller value of delta x, so if I take delta x equals to 0.05, then the number of nodes, of course, will increase. The number of nodes that I will use is 1 over 0.05, which is 20 plus 1. So I will need 21 nodes. And of course, this will make computational time larger. Yani, more you add nodes, the time of solution will be larger. That's why we say we need to compromise between accuracy and computational time. So it's good to decrease delta x, but if we decrease it a lot, then the time of solution will increase also. So we need to take a value of delta x that will give accurate result, but that is not, as much as possible, we need to not have it very small, because if it's very small, the time of computation will be large, and we can need days sometimes for simulations. So, and the number of time intervals required to carry the solution to a prescribed final time will also increase with decreasing delta t. Therefore, the computation time will increase with decreasing delta x and delta t. So the choice of delta x is typically based on a compromise between accuracy and computational requirements. And for example, if you reduce delta x by 2 and you just have a percentage difference in result of 1%, you say that since 1% is really small, no need to take smaller delta x. So if you see that the variation in solution is not high with a smaller delta x, you stop there. You say it's enough. So once the selection has been made, however, the value of delta t may not be chosen in an independent way. It is instead determined by stability requirement. What do they mean by this? Okay, so in general, first you select your delta x, and delta x will impose the value of delta t. How? We'll discuss together now. Okay, so in general, The explicit method has a disadvantage that it's not unconditionally stable. So it can give divergent results if we don't choose delta t in an appropriate way. In a transient problem, the solution for the nodal temperatures should continuously approach final steady state values with increasing time. So in general, to know if your solution is convergent, if you explore the variation of temperature with time at a certain cell, the temperature variation, okay, the temperature should approach steady state with when t tends to infinity. So with increasing time, should approach a certain value of temperature. However, with the explicit method, this solution can be characterized by numerical oscillatory behavior. Yani the solution can oscillate, go up and down, which are physically impossible. And this oscillatory behavior will become can become unstable. Yani you can have this in the solution. If you don't select delta t appropriately, your solution can be like this. So instead of approaching the solution, you will diverge from the solution. And therefore, this will cause divergence from actual steady state conditions. To prevent such errors, so these are numerical errors that can lead to divergence. And not any delta t you consider can reach the accurate solution. And we have proved, that in this type of equation, in the explicit equation, to prevent such divergence, the prescribed value of delta t must be maintained below a certain limit, which depends on delta x and other parameters of the system. This dependence is called the stability criterion, which may be obtained mathematically or demonstrated by a certain thermodynamic argument. Here, will not go into numerical details. If you want solutions on how we find this delta t, we'll just give you the result. Yani after doing analysis, okay, we have demonstrated that the criterion in the explicit method is determined by requiring that the coefficient associated with the node of interest in the previous equation is always greater than or equal to zero. Yani we demonstrated numerically that this equation will give stable results and will not lead to divergence if all coefficients are positive in this equation. Okay, so if you look at the following case, the coefficient of TMP plus 1 is 1, which is positive. The coefficient of TPM plus 1 and TPM minus 1 is the Fourier number, which is also positive. We have only possibility of getting negative results for the coefficient TPM. So to ensure that we'll not have divergence, we can put the following condition. We can say that 1 minus 2 Fourier should be positive. And if we replace Fourier by its expression, so 1 minus alpha delta t times 2 over delta x squared should be positive. So this will give us, if you want, a certain limit for delta t. So I can say that 2 alpha delta t over delta x squared should be smaller than 1. And this will impose a limit for delta t. Okay, so delta t in this case should be smaller than delta x squared over 2 alpha. So once you decide for the value of delta x, you can determine the limit for delta t. Okay, so and this will correspond, if you want, to Fourier number smaller than 1 over 2. So we can say that in case we have 1D, in case we have 1D case, the condition for Fourier number in order to have a stable solution is that Fourier number is smaller or equal to half. But if you go now to the 2D equation, you have a different condition. Because if you go to the 2D equations that we transform to numerical form, the coefficients for Tmn p plus 1 is Fourier positive, it's fine. And the coefficients for all of the other cells, adjacent cells, Tpm plus 1n, m minus 1n, mn plus 1, mn minus 1, the coefficients are equal to Fourier, which is positive. And here the coefficient is 1 because we divided by Fourier, it's positive. So we only have a possibility of a negative coefficient for Tpmn. And for 2D, this coefficient was proved to be 1 minus 4 Fourier. So the condition in 2D case, transient 2D case, without generation to have a stable solution is that this term should be positive. So in this case, the Fourier number should be smaller or equal to 1 over 4 to ensure a stable solution. Okay, so the criterion defined is always to have positive coefficients for our terms from this side, from the other side of Tp plus 1. So since the only possible negative coefficient is for Tpmn, we put a condition that this coefficient should be positive, and then we determine what is the criterion of stability. So in 2D, the condition of stability of solution is to have a Fourier number smaller or equal to 1 over 4. Now, if we apply, this method for different types of cells, you remember in chapter 4, we said we can have a cell at the center, we can have a cell at extremities. So together now we derived for an interior node that is surrounded by 4 adjacent cells, we derived the equation of Tp plus 1 Mn. Okay, and we said that the condition to have stability is to have the coefficient of Tpmn larger than 0. So in this case, for an interior node in 2D, the condition is to have Fourier smaller or equal to 1 over 4. And then if we want to use implicit method, so this is for explicit method. For implicit method, what will happen? As I told you, in implicit method, you will replace temperatures in the other side, in the second derivative. You will consider that all terms are at Tp plus 1. So this will give you another equation. And then in solve, you will express Tmnp function of temperature at P plus 1 at all other cells. But the solution here is not explicit. So you need to solve for Tp plus 1 Mn function of Tp plus 1 in the adjacent cells, which makes the solution more complex. Okay. Now, if I consider another type of cells, the cells at extremities, so they are subjected to boundary conditions. Okay. So, for example, if you remember, we have considered these cases in previous chapter, but the only new